Okay. So, in this class we will talk about epidemics. So, epidemics in networks. So, how is epidemics important for a computer scientist, like one who is doing research or development in network science, network engineering? Can you tell me? So, spread of virus. Okay, spread of virus. Any broadcasting can be thought as a epidemic phenomenon. Okay. So, when you are broadcasting, when you have Bluetooth broadcasting perhaps, okay. So, that is type of epidemic, okay. Or otherwise in wired we have flooding, okay. When you flood, basically it is a sort of epidemics. So, if you know the underlying epidemic models, or if you know the underlying epidemic methodologies, then it would be easy to understand how good these flooding techniques will work. Okay. So, the point is we will see that what are the parameters which can be controlled. Okay. So, in epidemics, if I think of a population which is undergoing some sort of epidemics, how can the population be divided? Okay. So, there will be some susceptible. Okay. So, there is a disease going on, some part of the population will be susceptible, that they may catch the disease. Okay. Tell me. Infected. Okay. So, some parts of the population which is infected. Okay. And can there be a third group? Huh? Yeah. What? Resistant. Yeah. Correct. Okay. Resistant. Okay. So, those who has gone the disease, perhaps who has got the disease and become resistant. Like if you think chicken pox, okay, you get the disease and you get resistant, or say you get AIDS, then it may be okay. So, you may be removed. Okay. Either you may get resistant or you may be removed. Okay. So that is why epidemics is thought as a SIR model. Okay. Epidemics is modeled based on SIR. Okay. Susceptible, infected, removed. What other model can you have? SR, you have to be infected. So, you can have that you are like in chicken pox, you are resistant for 8 years, then you again become susceptible. No, RS is a state, R is a state, that resistance state, it is not a property. Okay. Or you can have something like this, okay. SIS, okay. SIS, a typical SIS is gonorrhea like, okay. You may get infected and as soon as you get recovered, you are again susceptible, you do not build any resistance, okay. So, it is SIS, okay. So, these are the 3 basic models of epidemics: SIR, SIS and SIRS. Okay. So, what is happening? What are the parameters? There is a parameter beta and there is a parameter gamma. What is beta? That the probability, this is a probability per unit time of catching a disease. okay, probability of unit time of catching a disease. And what is gamma? That you become immune at some constant rate. Okay. You become immune at some constant rate gamma. Okay. So, there are two parameters, beta probability per unit time of catching a disease, and gamma become immune at some constant rate. Okay. So, now what we have to write? So, this entire population is sometimes becoming susceptible, sometimes becoming infected, sometimes becoming. So, we can write basically the rate of what will be what are we interested, that the rate of change of susceptible, the rate of change of infected, and the rate of change of refractory or resistance, okay, resistant. So, let us write ds dt is rate of change of susceptible. So, that will be probability per unit time of catching a disease minus beta into I, number of fraction of infected present, and S the fraction of susceptible present. Okay. So, it is minus beta I S. Okay. Okay. What is di dt then? Tell me. How many are entering per unit time? How many will be entering per unit time? All this which has exited the susceptible, where will they go? So, this is directly coming, and what is exiting? Gamma I. Okay. This is a rate. So, I is the fraction of infected present, and ds dt is sorry dr dt, dr dt will be okay. So, this is a situation where what is the I infected, where I, that one, this infected number of so I have a rate. So, that rate would depend upon how many infected people are there. Okay. So, if I get, if I have a rate of catching the disease, and if 2 people are there, that rate doubles, okay, because I am constantly getting input from 2 person. Okay. S is that how many people are present, how many people who are susceptible. Okay. So, that number, so for 1 person this is the rate, and how many persons are present? S persons are present. So, S into that rate. Okay. So, these are the 3 equations which you are getting. So, once you are getting 3 differential equations, you can basically, what can you see using this? So, just think, see the first equation, we need not solve it, but ds dt is equal to minus beta I s dt. Okay. So, okay, this will give us ds is equal to minus beta, what is I? 1 minus s? No. Okay, let us think I as constant. I will not do it, but I is equal to 1 minus r minus s. Okay. Yeah, that is an assumption which again we are working on large systems. So, yeah, fractions, but the amount is huge. So, there is what you are saying. Okay, so this is a good question. What is called? This is called basically mean field equation. Okay. So, this solving is called mean fields equation, and where we think that the entire solution is very well mixed. Okay. Entire solution is very well mixed. What does well mixed means? That I, S, everything is very independent, but what will you will see in fact that if there are some i's here, the i's will increase this way. Okay. This will be the normal thing. It is not that there will be some I here and there will be some I here and there will be some I here. Okay. Immediately there will be because of the short long links of the small world, but generally it will have a progressive flow. But in the well mixed solution, what you are saying that the location of I is not important. Okay. So, everything is well mixed, and so the point in differential equations is the point in differential equation you do not have ds dx. Okay. In a ordinary one dimensional ordinary differential equation you do not have the x component. This is the general problem of differential equation, you have just ds dt. Okay. So, if you have to consider the x component, then you have to put the partial differential equation, which we do not do. Means I am just telling you that you do dt then dx. Okay. So, anyway, so these differential equations will give you one important thing, it will give you the progression of disease, time spectrum. Okay. It will give the time spectrum of progression of disease. Okay. SIR model is simple. SIR model tells you that at certain point everything will become resistant. Okay. At certain point, because so everything is going out from susceptible, nothing is coming in, while everything is entering resistance. So, the resistance model will increase. Okay. Anyway, so now the next question is what has it relation with networks? Okay. So, immediately when we talk about networks, the well mixed concept breaks down. Okay. Because network has a structure, and the what does well mixed means in terms of network sense? What type of not all nodes are identical, fully connected network. Well mixed actually means that every node, it is a click. If I think in network stuff, it is a click, but networks are large and sparse. So, all the networks which we consider are large and sparse. So, full mix solution does not help. Okay. So, now can you tell me what theory which we have studied till now can be used to model epidemics? What theory can be used which I have studied? What theory we have studied till now? We have studied the percolation theory. Huh? What does percolation theory tells us? What does percolation theory tells us? Huh? Formation of giant component. Okay. So, that was our basic, and I think we did a extensive formation of giant component. Okay. So, again if you forget, I will show you this picture. What does percolation theory say? That this is a graph, okay, this is a two-dimensional graph, and connectivity from each to each has some probability. Okay. Connectivity between a pair has some probability. Okay. This is a lattice. Okay. It need not be a lattice, but I am taking a picture with a lattice. As you see, when p is equal to 0.315, what happens? This is not connected. Okay. This is not connected. While as you increase the connectivity, you see at p is equal to 0.525, the entire thing is connected. You can find a path from here to almost here. Okay. So, what is happening? It is not depending upon how meticulously you put the links, or it is not depending upon on the shape exactly, it is just depending upon the p. Like very important example is how water get boiled. Okay. So, in water getting boiled, it does not depend whether you put it on a saucer or you put it on a big bucket, it does not depend, everywhere you get it around 100° centigrade. So, the temperature is called the order parameter, which is independent of the underlying activities going on. So, here also same thing happen, that when p is equal to 0.35, it just depends upon p. If you go on increasing p, as at certain point you get a giant component, which we have termed again and again as giant component. Like I think I gave you an example that when water drops initially, you will see that there are small clusters, but after certain time you will see the entire thing merges into one. So, this is what is called percolation theory, okay. And this is what helps us to identify giant component. And so, how is it related with epidemics? How is it related with epidemics now? Tell me. Yeah. So, what happens is, what are the two parameters we have? What are the two parameters we have? We have the parameter beta and we have the parameter gamma. Okay. We have the parameter beta and we have the parameter gamma, and we have the topology, say pk. So, these are the three things we have. We have parameter beta, parameter gamma and the topology pk. So, at what value of beta and gamma would the topology, would the disease spread to, would the disease be affecting a sizable portion of the entire network? This is the question. Question is clear, that at what parameter of beta and gamma, given the topology, a sizable portion of the topology will get affected by the disease. Clear? Okay. So, there are many models which do it, but what first let us think what we have to do with this beta and gamma. Can you tell me what we have to do with this beta and gamma?
You have to find the relationship between them, so that if the ratio is less than some number.
With what? Beta and gamma, we have to find the relation with what? See this and tell me. P. So, we have to somehow relate beta and gamma with P, because P is the order parameter. So, you have to convert beta and gamma to the order parameter. Okay. So, there are many techniques which do it, but I will just these things I will just write it. We could have done it extensively if it was a 4 credit course, but Okay. So, this is how you write it, that so you how many so you have it and you have a neighbor, this is a node and this is a neighbor. So, the point is the point is this neighbor would be susceptible, this neighbor would be susceptible is depending upon a distribution, any distribution, the neighbor will be susceptible depends upon a distribution, and recovery rate also instead of just gamma depends upon a distribution. Okay. Recovery rate instead of a gamma depends upon distribution, and e to the power minus beta gamma means the beta would actually help in forming the link, while gamma will actually decrease the link. Okay. So, this way things have model. So, let us believe this, and now can you do you remember that how do we calculate giant component? We calculated giant component by first enumerating the average component size. Okay. So, this I have instead of P I have told T, okay, it does not matter. So, what was happening, if you remember that here this case the average component size will be something like this. Average component size of the network upon which this disease is going on. Okay. So, again when this network, when the disease is spreading, you will at first begin to have small components. Okay. Now, my question is, what is the average size of this component? And I think we did it extensively, but so the average size of component is this, it is found that the average size of component is this. Okay. So, now tell me, when does giant component arise? When this part is equal to 0. So, 1 minus T g dash 1 is equal to 0, that means T is equal to 1 by g dash 1. Okay. What is g dash 1? So, G01 is average T. No, Z01 is not average G. Z01 is 1. Yeah, Z0 dash is 1 and G1 is
number of nodes, number of neighbors reached from an edge.
Number of neighbors. So, it is if you pick up a random edge, then the number of neighbors which you reach. Okay. So, that was essentially pick up a node, then pick up a edge. Okay. It was same, that if you pick up a random node and pick up a random edge and then reach, what will be the number of neighbors, outgoing neighbors. Okay. So, anyway, so what is happening? It is basically the second part. Okay. So, TC, what is TC then? TC is the critical probability which will be needed for epidemics to shoot. Am I clear that T is this P, and now I know that to have a giant component, that means to have epidemics, this equation should hold, and from there I get a critical TC. Okay. That upon that only giant component will shoot. Okay. And what is G dash 1 in power law? If I have a power law network, what will be this? What will be the second moment in a power law? So, remember this, in a second moment, the second moment of a power law always diverges, that means it becomes infinite. Okay. So, if it becomes infinite, what you can say? Karishma, what you can say about TC? Huh? Yeah, so what is the value of TC? Huh? Yeah, 0. So, anything, so what does physically that mean? That even if one has a disease, even if I have a disease, in a power law type of situation, there is always chance of epidemics. So, TC becomes 0. That means what? Even if one person Orithro has a disease, everybody will begin to have the disease. Okay. Okay. ठीक है? Okay. Some other important result which I think I have told you before also. The important result is that how to vaccinate. Okay. So, what is the most so how to vaccinate? How to vaccinate is related with what we studied in this previously? Huh? No. It is somehow related with centrality, but something else which we have studied. Is breaking down of the network, if you remember. Okay. The attack on network. So, it is simply related with attack on network. Why? Because if I vaccinate, it means I am attacking the network, and what is the purpose of vaccinating from a percolation theory point of view? Breaking down the giant component. So, why do I vaccinate? Means I can have a entire vaccination of the entire population like polio. Okay. That is always possible. Otherwise, you have a targeted vaccination. Okay. You have targeted vaccination of what we call, sometimes called, is core group, which people who doesn't know network theory, complex network theory, they even know how to vaccinate, okay, and they call it core group. Okay, core group vaccination. So, what happens is that you vaccinate the highest degree node perhaps. Okay. What you vaccinate? You vaccinate the highest degree node. Okay. Now, what is the difficulty with this? Finding the highest degree node. Okay. Finding the highest degree node. So, then what is the technique used in vaccination? What can be the technique used in vaccination? We know that a node is reachable. If I pick up a random edge, a node is more reachable if it has high degree, because reaching it is proportional, reaching a node is proportional to its in degree. Okay. Here we in degree is degree, but we say because how the number of paths it has, that helps in reaching that node. Okay. So, then what is the technique which you can use? Pick up a random node and any random person Arpit, okay, and then vaccinate his any random friend. Okay. Vaccinate any random friend. So, this immediately will ensure that you reach a higher degree node, because what we think that our acquaintance network is also power law. Okay. So, you pick up a node and vaccinate one of your random friends. Okay. Very good. Okay. Now, we come to the SIS model. So, SIS model is what? It has only susceptible and infected. So, as soon as you get cured, it is not that you build up a resistance, you are susceptible. So, can we write the rate equations? ds dt will be minus beta is plus gamma I. Okay. They are removing, but that removed people are not going to the resistant mass now, they are coming back to the susceptible mass. And what will be di dt? This will be plus and this will be minus. Okay. Okay. So, now what is the can you predict a steady state condition? Can you predict a steady state condition? Huh. S equal to? No.
The rate of change is 0.
So, first is ds dt equals to 0. Okay. So, that means minus beta is plus gamma I is equal to 0. So, I minus beta s anyway. So, s is equal to gamma by beta and I is equal to 1 minus gamma by beta. Okay. So, you see that there is a endemic, this is called endemic situation. I is 1 minus s. So, I have taken the fraction, the population only has I and s. Okay. So, important thing you will see that खुचली कभी नहीं जाता है. Yeah, this is very, it may be laughing, but this is very important that you see this happens. You have a steady state condition, and if you pick up random people and see the number of people, you will see it follows this. Okay. Huh? It will? Yeah, you can never cure it. Okay. 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 So, now we talk about in terms of networks. Okay. So, I have a node okay. I have a node n. What is the in there what I have written beta, what is beta I? What is beta I essentially? In this equation ds dt minus beta is plus gamma I. What is beta I? Yeah. So, for a particular node or particular agent, what is the rate of infection? Okay. So, now this is the node, okay, in the network. This is the node in the network. So, can you tell me what will be beta I in terms of this node's property? What will be the first most important thing? K. So, K. Okay. So, K is important, that how many connections you have. Okay. And then the probability that the other side is infected, or the probability that the other side is infected, and the infection rate. Infection rate, it is not that, yeah, means you, it is not that at any contact you will with the AIDS person you will get AIDS. Huh? It is 1:100. Huh? If you have 100 wrong contacts, you will get AIDS. Okay. Okay. Yeah, probability that may not work with you. Yeah. Okay. So, what happens is K lambda. So, this is basically this Bi. Okay. Why do I do this? Why do I put theta lambda parameter of this function theta? It depends upon the infection rate. It depends upon the infection rate, that how many of the other end of the node will be infected. Okay. So, then we can write dik dt is equal to k means actually what was there, di dt is equal to beta is plus gamma I. I have taken gamma is equal to 1, okay, and s is equal to 1 minus I, and written this. Okay, and it is just for the kth node. Clear? Any problem? Okay. So, at steady state, I k is equal to I just okay. How do you find the steady state? Dik dt equal to 0, and this gives you this. Okay. Okay. So, then what will be I? What will be I? No, this is ik. So, what will be I? Summation of. So no. What will be I? Ik into pk. Okay. Okay. So, that is k. Okay. Okay. And what is, let us think what is, what did we say this is? What is this? The probability or expectation that the other side of the node is infected. That means what? Basically average numbers of infected. The expectation that other side of the node will be infected. That means average number of nodes that is infected, and that is equal to
A into I. It's not just the average number of the entire network, average number among its neighbors.
Yeah, but I do not have this as this. I do not have as a case. So, I have to take the average number of entire networks. So, this is again what we call, very good question. So, this is again what we call is mean field approximation here. Although we are doing networks, but there is some mean field approximation. What is the mean field approximation here? That all those which has been affected has been equally distributed among all degrees. Okay. All those which have been affected are equally distributed among all degrees, which may not be true, which will not be true. Okay. Okay. So, then tell me what will be this? What will be this? Ik x average number of. So, it will be k pk ik summation 1 by z. So, z is the average number and you have this many number of neighbors, all those of them, how many of them are affected, this many of them are affected. So, summation and divided by the number of neighbors. Okay. So, this is again 1 by z summation k pk ik. Okay. So, what is ik? Ik is this one. Okay. So, then this becomes summation k pk. So, k square is becomes ik. Okay. 1 by there is a 1 by z. Okay. So, this is clear. So, theta, so this 2 goes because this is summation over k and this is not depending upon k. Okay. So, what happens? 1 is equal to 1 by z So, essentially I can take this also out, okay, I take this is also okay. Now, what is pk? Pk is a power law. Again we can think as it is the Barabasi model, let us think. So, this will be 2 m square by k, okay. It is the Barabasi model. Sorry, k to the power 3, very sorry, okay, it is k to the power 3. Okay. So, means what have I got, what is the least value in a Barabasi model? M. So, is it is always m or above, okay. So, then you have lambda z, you can have k is equal to m to infinity k square pk, pk is gone, pk becomes 2 m square by k cube k square 1 plus k, I write it 2 m square by k into 1 plus k. Okay. So, this should give you what? It will give you because this is the only parameter which is left, okay, which is independent of k, and you will get this as, let me write it here. So, you will get e to the power minus 1 by m lambda m 1 minus e to the power 1 by m lambda. Okay. So, now what is rho, what is I? What was the formula of I? Again. So, I write this formula once more, is summation of k lambda. So, this 1 plus k and pk we know 2 m square by k cube. Okay. So, this is I. Okay. And we also know what is lambda, what is theta now from this. So, then I is equal to basically m to infinity 1 by k cube 2 m anyway. So, I is equal to 2 m square lambda okay. And through some calculation what we see I is equal to is proportional to e to the power minus 1 by, through some calculation you see is I is equal to e to the power minus. So, what happens when lambda is equal to 0, means infection rate is very small, what is happening? even then this will not vanish, I will not vanish. E to the power minus infinity, e to the power minus infinity is tending to 0. Means, so, okay, but as soon as lambda becomes greater than 0, I also becomes greater than 0. Okay, limit. So, what is happening is that again if somebody gets the disease in a power law, this has immediate potential of forming an epidemic, means there is a non-zero probability of, means it, see this again I will come back to this equation, just this last equation, see this equation, what has happened, when is it, when is this stable, when is this stable, when I is equal to 0, that then also this is stable, this is equal to 0, this equation. So, as soon as I increases a little, then it will stabilize only at this condition. Okay. So, that is also somehow getting reflected in a power law network. Okay. Thank you very much.